Hello and welcome back to the Envirohealth podcast. I'm your host, Emily Muller, and today I get to sit down with Dr. Tim Lucas and talk about his work in statistical and mathematical modelling for studying diseases, and we take a deep dive into a recent project on malaria. Please note that some of the audio is a little bit scratchy given it was one of our first ever podcasts, so please bear with us. Thank you so much for joining us, Tim. We're really happy to have you here.
Thank you for having me.
So we typically ask our guests this first question. What are you looking forward to?
I guess two big things coming up. The first is starting a lectureship at the University of Leicester at the beginning of July. So that'll be very exciting, going from, a long string of short-term positions to a permanent position. Very excited about that. And then just continuing my current work, bringing kind of human movement and geostatistical models together. I'm excited to see where that sort of develops from here.
Okay, I look forward to actually hearing more about your pollution work. And congratulations on your role at Leicester.
Thank you.
So maybe we can also just kind of find out a bit more about the journey that you've taken in academia. Kind of, first of all, getting into science. Like, how did you even make that decision from a younger age?
Oh, from a young age, that was watching David Attenborough as a kid and, VHS tapes of whatever his first big series was, watching those until the quality degraded and the whole thing fell apart. And then, kind of cliche stuff, but from those early years of watching David Attenborough, it felt fairly clear and easy to me that I wanted to do some sort of biology. So, yeah, that early stuff was relatively straightforward, just oh yeah, I'll do biology at A level. Oh yeah, I'll do zoology at degree level.
And from your undergrad studies to your PhD working on malaria, the Malaria Atlas Project, what was sort of the transition from undergrad into postgraduate research?
So that was definitely less obvious. So my undergrad was zoology, and then it was one of those integrated masters and undergrads. And so just going into my project for my master's year, a supervisor I'd already worked with said, I've got this interesting project. It's on malaria. At that point, I knew really nothing about infectious disease, but I liked maths and I liked biology. And so then from there, just very first, he said, here's a project. Do you think it's interesting? So I went and looked up SIR models and I was like, oh, that's really cool. I was really into that kind of dynamic systems modeling at the time. So I took that project on. And then doing that project made me realize that I enjoyed disease. So projects before that, I'd really struggled. That first paragraph of a write-up was like, why is the evolution of cooperation important? Or why is conservation important? And then this malaria one, I was like, 500,000 people have died of malaria each year. Done. And that was just, I really enjoyed that very clear application. So that made me realize I wanted to study disease, but I was still interested in this kind of interface with sort of ecological systems. So my PhD, I went to UCL and did bat viruses and zoonotic diseases and didn't, in the end, given the year we're in, I probably should have published a paper that said coronaviruses are going to spill over into humans sometime and I'd now be famous, but I'm not. My PhD is utterly unread. And then, from there, I realized that I preferred statistics to dynamic systems, and so moved towards kind of spatial modeling of malaria for a postdoc.
There seems to be this kind of thematic thread of kind of modeling, mathematics, whichever sort of place that it's applied, which I suppose a lot of researchers will resonate with this, deep satisfaction from technical work, but at the same time wanting to do something which is meaningful and has kind of a relevance for people's lives.
Yeah, exactly. But I guess it's more often to meet people that did a maths degree or did a statistics degree and then are kind of looking around where to apply those skills. I suppose I haven't met a lot of people that did zoology or biology and then did that same path. That's relatively unusual, I guess, but that's fine.
I don't know if we're allowed to talk about this, but given the fact that the US is investing so much money into researching the escaped from the lab theory of coronavirus. What are your thoughts on this?
I definitely don't have any careful thoughts, but spillover from a wild population seems very reasonable to me. There's no reason. It was utterly expected. We've had multiple spillovers. We're going to have many more. It is not surprising that a virus would have spilled over from a bat into human populations and spread. So
what about from the lab?
I have no idea. I don't know anything about labs. I haven't been in a lab since undergrad. During my time at the Malaria Atlas Project, I was in a building with labs and computers, and like the floors were different in the rooms with labs, and I wasn't allowed on the shiny floors. I was only allowed on the carpet floors. Like, I don't know anything about labs. I don't know anything about Chinese virus lab research. So I have no idea. My priors on that are nothing. I don't know whether that's likely or unlikely. All I know is that it's not at all surprising to have zoonotic spillover.
Okay, fair enough. I guess there's something I'm interested in. You've kind of got this very broad remit of research, people that you're working with, and interests, I would say, from the work that you've done. I think a particular piece that you did last year was unit testing in epidemiological modelling, because obviously there was some flurry around these models which have been sitting around for like 10 years or so and not being checked and not being tested. And personally, I remember seeing a tweet once, and it was somebody saying, as a PI, how often do you check your students' code? And this was a shock to me that there were labs in which this was taking place. Like, the PIs were checking students' code. And I think as we're more interdisciplinary in the makeup of what we're doing, I know for myself, and I even come from a mathematics background, but like, I don't have a training as a software engineer, which is what I'm often doing day to day. And I can imagine even people that are more on like the health side of things, they definitely aren't having training in software engineering. So would you kind of like advocate for, if you're going to be sat in this interdisciplinary scientific world, like, we need to have adequate training across the spectrum?
Yeah, I think absolutely it's so. And lots of these things, the first steps of something like unit testing is not difficult. If you can write some R code to fit a model, you can also write some R code to run a unit test. It's not some super conceptually difficult thing. So we definitely should be doing that training to say this is a thing that you can do and you should do it. We should definitely have sort of, it should become the norm, and it should be, for example, a question asked at sort of peer review stage and various other stages, that, there should be some barriers where if you haven't sort of done a reasonable job of testing your code, you'll at least sometimes butt into these barriers and be like, oh, okay, I should have done that. And then I think a lot of it is this kind of lab culture that PIs should be pushing it on their supervisees, and unfortunately that isn't the case in most labs yet.
But also typically PIs might not necessarily have the necessary know-how with respects to certain elements of like software development as well, right? So should there be like a university-wide approach to say, okay, like, here are all the courses. Actually, Imperial's really excellent at this at the graduate school. They have constantly have these courses on how to, buffer up certain skills. But I guess, should it be more integrated into the training, just generally?
Yes, and I guess it depends what level you're talking about. For example, my undergraduate zoology, we did 1 week of R per year maybe, and much as I like to advocate for more statistics and more software training across the board, I know it's going to be a tough ask to sort of start getting these big, deep software engineering courses into zoology undergraduate degrees. That seems like that's not going to happen. But definitely, I think having it available, all universities having some way available for people to go and learn, like from PhD level, it should be you start your PhD and then your supervisor says, there's the course on basic software engineering or basic like scientific programming. Go do that course, please. That's, week 1's turning your computer on. Week twos doing that course, and then go from there. And then a lot of these things, once you've got a couple of like PhD students or a couple of postdocs in the lab that know how to do it, then the culture starts building up. It's getting those first few in that makes it difficult.
With respects to kind of, okay, so those are the technical aspects. With respects to more the, I guess, softer skills one needs in the academic environment, and I know from just looking at some of the work you've done, you worked on the Global Burden of Disease project, which is, I mean, huge number of people, collaborators. So what are some of the challenges of collaborating on these huge projects and rewards simultaneously?
Okay, so I guess, so in terms of working on the Global Burden of Disease study, I was very much a small cog in that, and there's quite a large, I don't know what the word is, tall hierarchy. I reported to my line manager, he reported to our lab boss, the lab boss reported to someone at Washington, and they reported to Chris Murray. So, there was no sense of me collaborating with like people in other diseases, particularly, for example. It was very much
like modular.
Yeah, so I absolutely collaborated with all the people in the Malaria Atlas Project, and that was a very collaborative environment and a wonderful environment because of that. But in terms of those humongous collaborations, I was a small cog, and I sort of, to an extent, did what I was told. Mm-hmm. I can see having worked in that project, I definitely see that there's no way a small group can do that same project in any sort of good way. Is kind of what I've got to my thought process has led me to, that it's just impossible for a lab of 10 people to do a study on the global burden of disease that has any sort of kind of ability to compete with that. It's so much of it is data. It's collecting just endless data from endless collaborators, and so I think that is the clearest benefit of collaboration on that study is that you just cannot put together the data sets you need with a small number of people. It just doesn't work. I think. So I'd happily talk more about the sort of more direct collaboration I had in Malaria Atlas Project, if that's interesting.
Yeah, I mean, if the things that you think, especially from the perspective of people that are kind of like early career researchers, moving into these spaces, moving out of PhD and into these like bigger collaborative environments, especially if you think that there's sort of highlights or lowlights of that work.
Yeah, so and that definitely was, I guess, having just said that interdisciplinarity is assumed, Malaria Atlas Project was very interdisciplinary. They had a very good hiring policy of they would hire very clever, very numerate people, even if they didn't know epidemiology, and then they'd hire very strong epidemiologists and let those people work together rather than trying to find necessarily jack of all trades, although I was one of the jack of all trades. And it just was kind of this interesting approach of working with people that could understand maths, that it would take me a month to read some of these papers, for example, and they'd understand it in an afternoon, and then they'd, draw it on the board in a nice picture, and I'd be like, oh yeah, I get the intuition of that now. I don't necessarily need to understand the derivation. I can just go with the intuition, and I know how I can or can't use that in my work. So
that makes me suddenly just think that it would be great if there was just a person that would do that for all papers,
So, I mean, in computer science, there's some really great YouTube channels.
The 2-minute papers.
2 minutes papers,
excellent.
Yeah. And what's the blue and brown guy? He's excellent as well.
Oh, no, I don't know.
So there is stuff out there. There's also a lot of rubbish, so I guess that's the downside. But yeah, having really difficult stuff explained was wonderful. Also, it was just a really enjoyable experience working with someone that knew nothing sometimes. And, a super smart person that would learn this kind of statistical modeling that took me years to learn, they'd learn it in a week. But then you'd have to explain to them that, I don't know, mosquito nets make malaria go down, or like you'd have to explain that like, data isn't perfect in the malaria world, and that, it costs thousands of pounds to collect one data point. You work with physicists and they're often like, oh, can't you just collect 1 million data points?
Can't you just simulate the data and it should fit the model?
or just leave the machine on for an extra afternoon, and you don't need to do statistics anymore. It just either the dots fit your theoretical curve or it doesn't. And then you're like, well, no, you have to send a person to some village in some country that isn't the country that I live in. It's just a whole different world. And you're like, look, this is it. We're not getting any more data for 4 years. Work with what we got. And then and it was just fun, really different perspectives.
I think that's a good opportunity to move into talking about your malaria work. And I think what's really nice about it is you do kind of get this like introduction, like we were even speaking about earlier. It's important. Like there are many people that are dealing with this issue. Then we get to go into the methodology, and also, based on the sort of work that you're doing, which from my understanding is a lot of disaggregation. So how do you get this finer detailed maps of malaria? What are the potential outcomes for that? So I suppose from the health perspective, what do we know about the current state of malaria in the world?
So broad overview, 3-sentence overview of global malaria. Before COVID, it was like case rates were going down globally quite fast, but that rate of reduction was slowing down. So we were having all these worries about why is it slowing down? Is it sort of resistance? Is it various other mechanisms? Or was it that we were getting reducing it in the easy areas, and we were just getting to the point where we just hadn't made any impact on the populations that were difficult to access, and we had just made progress on the populations that were easy to access. So that's one thing. It's, the sort of the overwhelming numbers of malaria deaths are still in sub-Saharan Africa, but there is an interesting change in kind of the global strategy. So for years, the strategy was malaria is worst in sub-Saharan Africa. That's where we put all our effort in. And in the last kind of 10 years, 5 years, it's moved instead towards let's start at the edges where there's not much malaria and make it go from not much to zero, and then bring the map in. And I think that's a very interesting approach with some very obvious kind of trade-offs in terms of who gets ill. But that, for example, there's these ideas of sticky elimination in malaria, that once you've got rid of malaria completely, it then stays gone for quite a long time. Unlike, for example, coronavirus, where you bring in one person and suddenly you've got a whole new epidemic. With malaria, because it's mosquito driven, and so for one infected person to create one other infected person, a mosquito has to bite the infected person, then go bite an uninfected person.
Right.
Those first steps are quite difficult. So once it's gone from an area, it seems to stay gone. So anyway, I'm starting to ramble, but that's kind of an interesting change in the global strategy.
Joseph.
And then I guess.
Sorry. Joseph was telling us some interesting facts about the malaria in Europe. Like, it was not even that long ago that it was completely eliminated, right?
Yeah, so certainly in the Second World War, malaria in India and Italy was a big deal. The Nazis broke a load of dams in order to try and infect the Allied armies, for example. So, and we had it in Kent in, I guess, 100 or so years ago. So until the invention of DDT in, I guess, the beginning of last century, it was just quite prevalent over a lot of Europe. People our age have this sense of malaria just doesn't exist here, but it did. And with climate change, it could easily come back. That's the same thing. Not easy. It couldn't easily come back. It could come back, and we need to make sure it doesn't. And certainly less so malaria, but other diseases like dengue could easily come back to Europe, and so we do need to be watching that.
So I guess you mentioned these fringe areas, and if I'm not mistaken, the work that you published this year is really looking at these low incidence areas, which I suppose that to mean the fringe areas as this particular strategy. And the way in which we understand the prevalence and incidence of across the world. How you in the paper that you did this year, you talk about prevalence data and routine surveillance data. So what does that exactly mean, and who are we getting that information from?
Okay, so prevalence surveys, I guess, are the easier thing to explain. You send a team out to a village or a suburb, and you randomly sample 100 people and then take a blood sample from each of those and say, are you currently infected with malaria or not? And that's a prevalence survey. So it's also called sort of active surveillance. You're going out and doing something and collecting data. And to do that countrywide is very expensive, very labor intensive, and just logistically difficult. On the flip side, we've got this passive surveillance, or these kind of routine surveillance. And that is essentially where everyone that turns up to hospital and says, I'm ill, if they've got a fever, you give them a test for malaria, and every one of those cases gets written down and collated sort of at some level and sent into some database. And so it's very different in the sense that if you've got a health service and you've got a good disease reporting system already in place, it's essentially free. It's just a piece of paper added onto your... Yeah, it's free. But if there's not a lot of malaria cases, it's very good at collecting the few that there are, because you're using the entire health service to try and collect data. So in very good countries, if 2 people in the whole country get malaria, you'll probably know about those 2 people because it will be recorded and sent in. But on the flip side, if you don't have a good health service, if you don't have a good sort of disease reporting system, it's incredibly expensive to set up. And sure. You just cannot do that. Sort of like an NGO can't build a health system in a country. It's a long-term aim.
Presumably there's a significant urban-rural effect as well from countries in which actually there are facilities in cities for people to use, and kind of rurally health practices are very different. Yes. I mean, yes, there is urban-rural effects. And so we do try and account for that a bit. For example, in the Malaria Atlas Project, we did, I think Kate Battle led it, the whole project trying to predict if someone's ill, what's the probability that they'll turn up in this reporting system. And the distance to a city is one of the few covariates we've got that does predict that. So there is an effect. But also in these kind of middle-income countries, or to put it another way, in the UK, we're not just missing people that have serious diseases. It doesn't matter where you live in the UK. If you're very ill, you will end up in a doctor's or a hospital somehow. And the kind of the same is the case in a lot of these middle-income countries. If everyone has a car, and if you have a life-threatening disease, you will somehow get to a hospital. Yeah. So as you get to these richer countries, these middle-income countries, the problems become less severe in terms of rural problems. Just the data collection. All horribly exacerbated and confounded by the fact that malaria is very much a rural disease, though. So concreting the entire city is a very good way of getting rid of malaria anyway. Not a great way of helping people enjoy their urban environment.
No, but just more generally, concrete houses where there's no gaps in the houses for mosquitoes to get through makes a huge difference for reducing malaria. So all these very social and very disease-based things are utterly linked.
And I mean, even architectural, the materials that you have to build your properties and stuff, right?
Yeah, exactly.
So the paper actually, so the question that you're asking is, how can you disaggregate? Which you've asked before. There's another work that I've seen which was using variational learning to disaggregate. But from what I understand, the difference in this work is to say, well, how can you disaggregate when you do actually have ground truth prevalence surveys? So we spoke about the routine surveillance, which is, let's say in London, you might report it at level of borough in London. So now we've got 32 of those. I think it's 32 or 35. 32 of those in London. And how can we find out, is it, if we're in West London, is it like Imperial South Ken that has this high incidence, or is it Grenfell that has this high incidence, essentially? So how can you actually spatially localize the incidence? In the previous work, you were looking at disaggregating by either 5 kilometers or 1 kilometer, I think. But you didn't have prevalence data, right?
Yes. So other people developed the base disaggregation regression ideas, Hugh Sturrock and Someone Keel, an ecologist. So we used those ideas in our sort of global maps. We did disaggregation, but we didn't sort of invent those ideas. But then the paper I was doing was how do you improve that? From a
model optimization perspective.
Yeah, how do we make better predictions? Because this disaggregation problem is weakly supervised in a kind of machine learning word. If you have an area and you have a large area with one number for malaria in that area, you don't know which side of that area was providing all those malaria cases. So it's not as easy to learn the relationships between the environment and malaria from those data as it is. It's just not very easy. So it's I think it's an ongoing question. How do we improve this difficult task?
So this is my intuition about it, but please correct me if I'm wrong. So you have your covariates, which might be land use, distance to city, NDVI, various different covariates at the pixel level, which let's say is a kilometer by a kilometer. And you've got I think they're called bags in one of them, but you've got your aggregate malaria incidence. So essentially the models are trying to learn based on the covariates, based on the covariates of each of these different aggregate levels or bags that we call it. What is the relationship between the covariates and the malaria incidence? And by looking spatially at all of the areas which we have, we can come up with relationships between the covariates and malaria and then break it down again. So essentially we always have to have this summing process taking place. Like it always needs to add up to what we have at the aggregate level.
Yeah, that's exactly right. So I think it's useful to think of it in terms of, people say, generative models. How do we actually think this data comes to be? People in relatively small pixel areas in a country get ill and go to hospital and report that they were ill. And then me on my computer in London or wherever I live just get that final number. So that is the process. That aggregating, summing process isn't some arbitrary model thing. It really is exactly how it worked in real life. Someone on a computer added all those numbers together and sent it to someone else, and it eventually ended up to me. So that's the generative model. Once you have a generative model, you can always have a go at fitting sort of parameters in that generative model. But yes, and so there's this unclear thing of which covariates related with high malaria or low malaria. And I think one perhaps easy way to think about it, I'll say this is easy and then I'll explain it and do a terrible job. If you have one area and it has, say, half of its jungle, half of its desert, and it has high malaria, you cannot tell from that one data point whether it's the jungle or the desert that provided the malaria cases.
Right.
If you have two areas, say, one with jungle and desert and one with jungle and city, and they both have high malaria, you still can't really tell which of those types of areas provided malaria. If you have three data points, one with desert and jungle, one with jungle and city, and one with city and desert, if the city and desert provides low malaria and the other two provide high malaria, you can then start to learn that it's the jungle that caused the high malaria. That is the intuition behind it. So you need quite a few data points to start, or it can be difficult to learn unless you have quite a few data points.
That was a really good explanation.
So that's the intuition.
I guess it makes me think of one thing, which is obviously we have priors about whether or not it's jungle or desert. So do we also then, feed that into the model ahead of time?
We probably should. some of this gets quite difficult in terms of the fact that a lot of these variants are quite correlated, and we really have we kind of, in the Malaria Atlas Project, of which I'm no longer a part, but we kind of avoid these really causal questions because it is just incredibly difficult to answer these causal questions with the sort of observed data we have. And so we're asking predictive questions instead. We're saying, can we predict where malaria is, not what caused it? And so in that situation, it becomes less obvious whether you should feed priors in to these covariates, partially because if some of these covariates probably aren't directly causally important, but they're kind of a proxy for something else. Then you've got these correlations. So if you've got two correlated covariates, that if you fit a bivariate relationship between the covariate and malaria, if they're both positively correlated, when you fit them together, what will often happen is one of those variables will sort of be positive, and the other variable will be like gently negative, for example, and it's just sort of explaining the little bit of noise left from that first covariate. So if that's what it's doing, and if it's doing that well, then the priors aren't going to help you do that. And then finally, just often in these cases, just either we've got enough data that it'll overwhelm the priors anyway, or we have so little data that putting priors will just make the model will end up encoding our assumptions and nothing else. And it can be quite hard to get the balance there for those types of priors. We absolutely use priors for other aspects of the modeling. They're totally vital for the kind of random effects we use and things like that, the hierarchical sort of hyperprior components of the model. But for covariates, it's difficult sometimes to see how to usefully use them.
Okay, and so I know this isn't how it works, but the prevalence survey data, can it be thought of as this active learning component from the modeler's perspective, let me say, this active learning component where you could actually, so let's say in the paradigm where you're not including prevalent data in your model, to validate the disaggregation model that you have? Like, have you seen this before as opposed to including it in, but just to validate your disaggregation model?
So I haven't seen it be used in that way, and it definitely could be. We sort of did look at that a bit, and it's just often very difficult. There's a lot of noise sometimes in the prevalence data. Sometimes we fitted a model and then predicted prevalence, and just we had nothing, which was kind of awkward. And so yeah, it could be used for that, but that wasn't what we did. Perhaps another. But the way I guess we're using it is we've got this weakly supervised side of the disaggregation data. The aggregated data is weakly supervised, and the prevalence data is just normal supervised learning, and then we're doing both of those at the same time in one joint likelihood model. Okay,
so there's three different models that you compare, right? So the joint model, as you've described.
Yeah.
So the initial is just the baseline disaggregation, and then the second model is a baseline disaggregation where you have a Gaussian process on the prevalence point level prevalence data, and that's added as a covariate to the baseline disaggregation. So this is the definition of a Gaussian process, which I've pulled up, which is a probability distribution over possible functions that fit a set of points.
Yes. So I guess sometimes these words are used in a weird way, and I'll certainly use them wrong. But so what people normally talk about when they talk about a Gaussian process is they talk about what they mean is the fitted curve that they end up with at the end. And so what we were doing in that part of the paper was we were just fitting a spatial weakly surface to prevalence points to kind of summarize those prevalence points and kind of gap fill. Anywhere where we didn't have a prevalence survey, we now have a prediction from this wiggly surface. And then there's this kind of more technical side of it that I never quite understand, but you can also think of a Gaussian process as purely the prior on that wiggly surface. And so a Gaussian process is saying what wiggly surfaces would we see, because it's a prior on surfaces, which is a prior on functions. So saying what wiggly surfaces would we expect to see of those wiggly surfaces, which one does kind of fit well.
And we can just choose maximum likelihood one, as opposed to actually including the probability distribution over all surfaces.
So you don't even, I'm going to get this wrong, but it's not even the maximum likelihood. It's not really the maximum likelihood surface. It's just, I'm going to get that wrong, whatever I say there. But we're not using, so we're doing it in a fully Bayesian way most of the time. So we are averaging over multiple surfaces in a sense.
Okay, so you actually keep the distribution.
So one way of thinking about that is, if you do MCMC on the Gaussian process, maybe this one way that perhaps helps think about this. If you do MCMC over your data and over your Gaussian process, you'll end up with quite a number of fairly wiggly lines, and then the final kind of mean prediction will be much less wiggly because you've averaged over those fairly wiggly lines. So in that sense, it is quite important to be doing at least a fully Bayesian thing on it, because I don't know what maximum likelihood would mean in that context, but that would probably be more wiggly than it should be, because you need to average over the wiggly lines to get the less wiggly, good Bayesian posterior model.
Got it. We're keeping the posterior. Okay, so then let's get into the results, basically. So the joint model did outperform the other models in one of the countries. Was it Madagascar? Yeah,
wonderful Madagascar, where all models work.
Why do you say that?
It just is. I'm not quite sure what it is, but you do these. So I've done two similar papers, this one and another paper, and every time things work in Madagascar and things don't work in other countries.
Surely it must be a function of data, something like this, no?
So it may be that Madagascar is slightly higher prevalence than some, and has a very wide range of prevalence. So the highlands in Madagascar are fairly low prevalence, whereas the lowlands are fairly high. So compared to some of the other countries we looked at, say Senegal, nowhere in Senegal was as high as the high areas in Madagascar, but then it's just quite flat across the whole country. So it might be that, but yeah, things seem to work in Madagascar and things seem to not work elsewhere.
I love this idea of disaggregation. I can just imagine it being used in so many different fields, as opposed to, just malaria incidents. Are there any other application uses that given that you've also just explored loads of different data sets and substantive application areas, are there any other domains in which you think it could be useful?
Yes, that is what my fellowship is and what my future lectureship will be about.
Nice.
For my fellowship proposal, I guess this is useful to say for any younger people listening, or, less, whatever the word is, early career people. I'm currently doing a fellowship at Imperial on air pollution. I also applied for a fellowship, multiple fellowships for malaria, and didn't get any of those. But all those fellowships were the same idea of disaggregating over movement. So what we have is, if we go back to these prevalence surveys, they're kind of the simpler case here. We've got a person that lives in a village that does or does not have malaria. And normally in these statistical models, what we're doing is we're relating that presence or absence of malaria to the environment in the pixel in which their village is. And that's the only place we consider. We ignore everything that's more than either 1 kilometer or 5 kilometers away from their house. But of course, people move. It's, we're not trees, we're people that move. So that person is not just exposed to the environment at that house. They're exposed to the environment in the places where they work, the places where they visit friends, the places where they visit family. And so what I'm doing in my fellowship is trying to do that. So I'm saying a person in London has a disease, but they haven't just been exposed to one sort of element of air pollution, one measurement of air pollution at their house. They've been exposed to this kind of cloud, this distribution of air pollution values over the places where they went. And so it's the same idea then. We've got sort of multiple pixels that are all affecting this person's sort of single disease status. So
do you not only need mobility patterns, but you also now need this like small level estimation of exposure?
Yes.
Where do you get mobility information from?
So that's one of the difficulties with this work. So the data sets I'm working on at the moment, I'm using one data set that Sean Beaver has provided. So he took London travel diaries, London transport demand survey diaries. So someone said, yesterday I went from my house, I took a train, or I can't remember exactly what they said, but they said I went to King's Cross and then I took a train to Milton Keynes or something. So he's done a whole lot of work saying, well, given that we know where they live, that they went to King's Cross and that they went to Milton Keynes, we can therefore have a good guess of all the different places they visited in between those two spots. And then using various air pollution models, we can have a good estimate of what air pollution they were exposed to at any time. So if they were walking, they'd be exposed based on what the air pollution is on that road that they walked down. If they were on a tube, you've got decent estimates of what the air pollution is. So that's one of the data sets I'm using. I don't have any disease data for that, but I've just got all these kind of realistic movement patterns and realistic exposure patterns. The other data set I'm using is the COPE data that Ben Barrett has been collecting. So it's a cohort of people with COPD, and they gave them all GPS loggers and air pollution loggers and asked them to carry them around as much as they could, be bothered to do, as it were, as much as they felt like doing. So I've got that data. And so then I've got each day they reported whether they had exacerbated symptoms to COPD. So I have relationships between, again, this cloud of exposure, this distribution of exposure, and whether they had exacerbated symptoms that day or not. And so I'm trying to relate, that kind of, it's the same thing. It's disaggregation of risk or disaggregation of exposure, but on an individual level.
Okay, yeah, for some reason when you first mentioned it, I was thinking at a population level as opposed to at an individual level. But then I guess you have to come up with these classifications of how people move through London, like certain types of commuters or maybe even now with the pandemic, there's this whole new class of working from home, which has a whole different meaning to it.
Yeah, the hope is to move it to population levels as well at some point, somehow. Maybe take those transport.
What about the Google mobility data? Is that quite difficult for one to get their hands on?
I think it's quite easy to get your hand on, but it's quite coarse resolution. It's sort of at regional level, and it doesn't really tell you where people went. It tells you whether they went out or whether they went to a park, but you don't see which park they went to. You just know that they went to a park. Similarly, there's Facebook data that could be useful. A lot of that has restrictions at the moment that can only be used for coronavirus. I've got a data set that a previous colleague used in one paper years ago, and they basically just used credit card transactions to follow a bunch of people.
Oh, wow.
So that will be interesting.
I love that you glanced to the side as though you had like a hard drive next to you with the data set.
I do. It's on this hard drive, and it's too big for my laptop. So I have it on this hard drive and on a Google, archive thing. Yeah, I was looking at the hard drive, willing the hard drive to remind me what's in that data set.
It's one of my favorite things, just with cloud services and just the excitement of technology and I just have such appreciation for how data has to be stored and moved, and actually it needs to be written onto a piece of hardware. So even though hard drives seem so bulky and kind of old school tech, it's the essence of what it is. So I appreciate them.
And every now and then you get this kind of jarring reminder, I don't know, at the Malaria Atlas Project, we did a lot of our models. Towards the end, we did them on Google Cloud Compute. And it was like, this costs $1 if you're in Belgium, and it costs, I don't know, $2 if you're in Holland. And it's like, why?
So
it's like,
why?
Well, it'll be like, oh, electricity is cheaper in Belgium, or, some weird, boring, very physical reason that means it's in this place and not this place. Or,
interesting.
You'll just get these weird default servers pop up in the United States, and they're always in, I don't know, places you've never, a state that has not had anything interesting happen ever. Often quite cold places as well, because the heat is a problem in a data center. So they build these big data centers in cold Midwest or cold West states of the United States, for example. And it's, like you say, it's just very physical, and it's not a cloud, it's a computer somewhere.
That was the biggest lie.
Yeah. So yeah, I agree. It's funny.
Something that I want to plug in later, which we'll probably have to edit, is the results of our models, because I don't think we actually got to, how these performed. And we did say, the joint model performed really well in malaria, and maybe that's a result of the kind of data and the distribution of incidence itself. I mean, so for yourself going forward, would you just say, okay, well, actually, this joint model shouldn't be used in specific cases? Maybe if we're going to take this fringe strategy of eradicating malaria, maybe this joint model isn't the best approach in fringe places, but we can use it in the medium incidence and high incidence areas. However, I think that you did conclude that the model with the Gaussian process covariate on the prevalence did still perform better than the baseline in other cases. So having prevalence survey, even though it's having prevalence survey data, even though it's expensive to collect, can improve disaggregation.
Yeah, it definitely. I'm convinced that it can, and I'm not convinced that the joint likelihood model is the easiest or safest way to get that improvement. The prevalence Gaussian process model is kind of clunky. It's not sort of statistically beautiful or anything. It's you make a covariate and then you stick it in. And one of the benefits of that is that if that data doesn't help your model learn, then it's a very easy way for that a covariate is quite easy for a model to ignore compared to what is essentially extra response data. So yes, if I was in MAP and rerunning these global models, I think I'd do that prevalence Gaussian process approach. It's simple, it's easy, it's fast. It almost certainly won't do worse than not doing it. I think these joint likelihood approaches are definitely interesting, and they have potential. Just often when we're thinking about data, we're thinking about information, and all these sort of thoughts of priors and sample sizes and different types of data. It's all about information. And joint likelihood models is the way of putting more information into your model. But they are difficult and finicky. I've been collaborating with other people on sort of ecological mosquito models, for example, and they're finicky. They're difficult to convince yourself that they're actually making things better. Yeah, they're difficult. But I think I kind of hope that in 10 years' time I'm not sure what the breakthroughs will be, but just some more normalization of this kind of data fusion idea and using data from all over the place. It seems like a powerful idea to me.
I can imagine as well, this cost analysis where you're saying, okay, well, if we need to do prevalence surveys, what is the spatial resolution at which they should be conducted, in which areas should they be conducted, the frequency. So, if you understand from the modeling perspective, what is the minimum amount of data that you need in order to create, reliable maps, then you can say from the cost perspective, okay, well, how can we actually collect more data cheaply?
Yeah, definitely. And people work on those methods. Again, it becomes more complicated in the sense that a lot of this data isn't collected. So most of the data we use in sub-Saharan Africa is by the demographic health surveys.
Oh, yeah.
And they're measuring a lot of things. They're measuring HIV and nutrition and housing quality. And malaria. So, we can't go tell them that we need 5% fewer surveys in this country and 5% more surveys in another country, because that's just malaria. There's other things that they're measuring. So yeah, there's definitely interesting problems there in terms of how do you sample spatially.
Exactly.
How do you, is that extra survey useful? In terms of, is it giving you spatial information? Is it giving you information about covariate? Yeah. So definitely lots of interesting work to be done there.
All right. I'm super happy learning about this work as well. I think it's really, really interesting. So thank you so much for kind of taking us through and giving us the rundown of it. And it's also exciting to hear that we'll get to hear more about the methods in work coming up from your postdoc at Imperial.
Yeah, thank you very much for having me. It was good fun.